Alrighty, might get started. Good evening, everyone. My name is Anshul, and welcome to EEWA's first event of Semester 2. Off the back of our enormous success of our Future of Engineering series, we are really excited to present to you all today the future of power engineering. This series has been designed to engage all you engineering students, where we can show you where your futures in different fields can lie. I'm very excited to present to you some of the speakers we have today. First up, we will have Laurie Curro. He has over 35 years experience working in power engineering, particularly in power transmission and distribution. Currently, Laurie is the General Manager in Power System Services at Horizon Power. Please join me in giving a warm welcome to Laurie.
Would you like that or that? Cool. Should be ready.
No worries. Okay. Thanks for that. Can you all hear me? So what I'm going to do is I'm going to give you, I've been told this has got to be kept to 15 minutes. Just going to talk about some of the issues that we're facing as an industry at the moment. Focus particularly on microgrids, because microgrids at the moment is the topic that everyone wants to talk about. And why, I guess, power engineering, why there's definitely a future for power engineering. That's what I'm going to cover. David sent me an email saying make sure you cover these things, so that's what I'm covering. Just a little bit about Horizon Power. So we think that the WA has a unique opportunity for development of new technology, new approaches, applications in the power engineering area. What do we mean by power engineering? It's basically the use of energy, how it's generated, how it's transmitted, and how it's used at the other end. So it's the whole life cycle of the energy paradigm, I guess, if you like. And in the past, we had the traditional one-way flow of energy, which served us for 100 years. Edison and Tesla and all those guys that set this thing up, it worked well for 100 years. What's happening now is it's basically been an economics and a commercial change to the whole industry, which has basically driven a lot of issues. You don't have to look too far to hear the discussions in Parliament at the moment about the NEG and the impacts of that. You've got different sides of politics saying it will reduce prices, it won't reduce prices. What's it got to do with power engineering? Well, it's got a lot to do with power engineering because the physics behind it haven't actually changed. Ohm's law hasn't changed. And that's one of the issues that these guys tackle with half the time, and they think they know the answer, but they actually don't. So Horizon Power, we're a vertically integrated utility. We're the only one left in Australia. What does that mean? We generate, we transmit, and we retail. So we're a retailer in the regional areas. You guys probably don't see much of us unless you go to Carnarvon or the Pilbara or whatever, and you see Horizon Power ads on telly, and how to save energy and all those sort of things. Exactly the same as Synergy. So we're the only vertically integrated. That gives us lots of opportunity from a commercial point of view. We don't have a lot of customers. We only serve about 120,000 people, but we have a huge area. So the area there in the southwest is not us, we're the rest of WA. So we look after an area that's 3 times the size of California. But we've only got about 45,000 customers. So the cost management issues are our prime directive to try and deal with. But yet, we have to provide the same reliability of energy that Synergy and Western Power does here in Perth. So you can imagine the equation that we might have there. So from a power engineering, I'm going to take you back to economics and commercial issues, because the problem we've got these days is these graphs that you've got up here, and you're all engineering students, so you can work this out for yourselves really. But what's happening at the moment is that the cost of renewable energy is coming down. People are saying, well, look, instead of paying you guys 27 cents, I'm going to put renewable energy on my roof and save money. So that's great. That's great. But what happens to people like us is that our revenue starts coming down. And the other issue is this duck curve up here, which you probably should have heard about somewhere along the line, but I'll go into that in a minute. But This one down here tells us, is basically an extrapolation of some work that Bloomberg has done that tells us that in the next 10 years there's going to be a huge increase in renewable energy take-up, particularly in the commercial space, but industrial as well. So it's one of those things where the price signals are wrong and they're they're basically driving that sort of behaviour. What does that mean? That you guys will be asked to be to design systems, to put systems on people's roofs, to design power networks and whatever, knowing full well that half the time they're going to make a loss. And, you know, and who's going to pay for it will be the equation. At the end of the day, I think the big issue that you guys can deal with and the opportunity you have is to find a solution to that duck curve problem that we've got. So it's one of these things where sometimes we call it an emu curve, but just give it a bit of WA flavour. So what's happening is basically that top graph up there that's got 2012 is your normal daily load curve that you would see in any power system, give or take a little bit. With renewable energy and basically with the price of solar panels coming down, you're starting to get that belly coming down and less energy flowing through the network, which is great for those guys that, you know, can afford it and can put it on there. What's generally happening is that at night, however, the head of the curve is going up all the time. So two problems. One, the head of the curve determines the size of the power system you want. So we still have to invest. Still have to borrow money, invest it in the power system, but yet we're losing revenue because this thing's coming down all the time. So somewhere along the line that's got to give, and you hear Tony Abbott say, well, look, this neg thing ain't going to reduce prices. That's what he's talking about, because you're not actually addressing any of that with any of the stuff that's going on. All they're saying is don't put too much renewable energy. Make sure you have enough stable power stations or power generating sources to keep the power system going. This is fundamental to economic activity within the state, within Australia. Unless we get prices down, factories aren't going to keep going. It's all those sort of things, particularly electric intensive factories like aluminium smelters and all those sort of things like that need a lot of energy. So unless we bring the price down, that just means jobs. So this issue here is really an issue that it's right in your domain to solve and really has not been solved. And some of the issues you see there that could help, we can talk about demand side management, we can talk about batteries, we can talk about perhaps you know, wind turbines or other things, you know, that could help, but that issue needs to be resolved. Put it another way, you've got in your bill, pick up your bill one of these days, and what you'll see is a small fixed charge and a large variable charge. And people try to bring that down, but the other side of the equation is the actual cost. Most of it's fixed, and you've only got a little bit of variable stuff. So as you guys use less energy, it just brings that variable cost down, but it brings your charge down quite a bit, and all of a sudden we're making a loss. In some of the networks that we run, it costs us about 70 to 80 cents to generate a unit, and we get 27 cents for it. There's nothing we can do about that. That's the equation that we're having to deal with there. And as more and more people put more and more solar on in those towns, that equation just keeps getting worse and worse and worse. Who pays for that? It's the people in Perth who basically can't afford to put solar panels on their roof. So it's the bottom end of the, you know, the social demographic that has got no option but to pay the electricity bill. That equation is not sustainable and needs to be dealt with. So I'm talking a lot about costs here, and what's that got to do with power engineers? It's really finding solutions to how we can deal with that duck curve issue, flattening out the load profiles, finding other technology that can deal with the energy flows around the place, so that we can bring those fixed costs down. These sort of things you've probably seen. Where are we at the moment? There's quite a lot of development happening in a lot of spaces. Advanced metering, smart inverters, all that sort of stuff is out there. We're inundated with data at the moment. We don't know what to do with it half the time, but do we have the right data? Do we get it on time? A lot of times, no. So there's a lot of advances that could be done there. And metering we've actually got smart meters throughout our network. Western Power couldn't afford it. The government won't give them the money at this stage. But we were able to do it because it was costing $70 to read the meter. 1 meter reads $70. So we had a business case that we could do it, but it's giving us a lot of data where we can do a lot of things with it. Home storage, distributed solar, those sort of things are now out there. Digital apps. So as your kettle comes on, you can pick it up on an app now and it tells you how much it's costing, all those sort of things. They are useful in one way or another, but until you get control of some of these devices, you probably can't do much with it. Smart appliances, I've been through all that. Trading platforms, there's a lot of discussion about trading platforms, peer-to-peer trading, blockchain, all those sort of things, Bitcoin. How useful that stuff is, I think remains to be seen just yet. We don't play in that space. But people, and my view is if people think you're going to be trading 1 kilowatt of energy one way and then sending it back the other way and there's a trading platform to measure 27 cents, I think they're fooling themselves. I think the issue is that energy will actually become quite cheap, free. It's actually the ability to connect to a network that costs you the money and get the reliability and the backups that you need. So maybe there's some work that could be done here. And again, it's all to do with understanding how power flows go, understanding load profiles, understanding customers, all that sort of stuff, which is right in the domain of where you guys sit. All this other stuff down here, into cyber security, big problem. We get hacked, 1,000 times a week on our website. So big issue because our SCADA systems, our telemetry systems are vulnerable to that sort of stuff. But safety management systems, there is more and more requirement to make things safe. You hear of incidents, you hear of all sorts of issues where, that poor girl in Belden, they got a zap off the tap. I mean, those sort of incidents just should not happen. So there's more and more onus on people like us to make sure they don't happen. How do we make sure they don't happen? Technology. We need technology to help us find those things before they actually occur. So there's heaps of areas that the power engineering area can get involved with. I don't know how long I've got, but I'll finish very shortly. This is a projection that you can find projections like this all over the place. This is one we've done where it basically says by 2050, 65% of the energy flowing to customers will be generated within their own premises. But they still need to be connected to a network. So how does that all work? How will the pricing work? How will the network stability issues work? You've got all sorts of codes that regulate power quality, voltage profiles, all that sort of stuff that needs to be made sure that you're within certain bands and it's measured and all those sort of things. So at the end of the day, if something goes wrong, you're the one that cops it, or the utility does. So again, how do we, how do we justify a lot of the stuff that we need to do to make sure that we don't go outside those bands? Or do we change the standards for appliances where you actually allow those bands to be, at the moment, we're looking at a change from our 240 volt plus or minus 6% to 230 volt. And the argument that's happening at the moment is that should that be plus or minus 10% or plus or minus 6%? Lots of reasons why both directions. Europe has gone plus or minus 6%. I think parts of Asia have gone plus or minus 10%. It's one of these things where it depends on your network and the risk you're prepared to take. But when you look at the appliances, what appliances will suffer from that? It's usually motor-driven stuff. So because all your power supplies can operate off 110 volts if they had to. So there's an opportunity. Widen those bands, make the networks more flexible. So what appliances can be designed and how can they be modified to deal with that sort of thing in the future? But that's the sort of progression that we see. I've seen others like that. Bloomberg is one that I recommend you have a look at what they do. It's all pointing in that direction. There's no doubt about it. At the end of the day, though, you still need stability on the networks, and that's what the neg discussion is about. How much coal fire or high fault level generating equipment do you need on a network to make the network work, to make your fuses blow, to make all those things that need to happen, on a network. Microgrids, you could probably see networks like this everywhere. High penetration renewables and storage. Standalone power systems is another area that we now, on the edges of the network, saying, well, maybe it's not worth having a network. Let's have a standalone power system where we can supply your house, your farm, etc., through something that's not connected to a network. That's justifiable based on the cost of the network. And we're doing that right now. In Esperance, we've already taken 5 customers off our network because it's cheaper for us and it's actually more reliable for the customers. And there's all these things that are happening. I've talked about advanced metering, customer tools and information apps and all that sort of stuff. Multi-flow networks, the laws of physics don't change. They were designed for flow in one direction. You push energy back the other way and you find all sorts of issues with voltages and stability around that that need to be managed. But storage is the key one there that really is coming in and changing the paradigm of the whole power system. But what I'm finding now is that it's more and more control logic and control systems over the top of all that. And you're going to get to a saturation point where there's not too much control. So I think the clever thing is to work out a way where you don't need as much control. So I have nothing against control systems engineers, but it just costs money and it requires redundancy and all those sort of things which, you know, you need to find a clever way. Artificial intelligence is one way to get down those paths. Microgrids then work their way into what we call a federation of microgrids. So this is a big grid. It's going to be, in our view, it's going to be a bunch of microgrids loosely connected together. So how do microgrids apply to big grids? This is the way that'll work. You can have a cluster of houses within a suburb that basically operate as a standalone, you know, as a group as an entity. They don't need any energy from anywhere else. They generate their own, they store their own, but they still want to be connected to the larger grid because they want to get their frequency from the larger grid, frequency control, and they want to get their standby from the larger grid. But they generate their own energy, and that's why I'm saying the cost of energy may be zero down the track. It's the actual cost to be connected that's different. So developing a model, understanding the physics around that and developing a model to deal with that is another opportunity that you guys have. So the summary piece is really around some of the stuff that I've spoken about, and I've only touched on some of this stuff because I know we could be here for days talking about this. We are at a crossroads, there's no doubt about it. The power industry issues are in the media all the time now. I think when you get beyond the hype and you go down to the basics, it's all about energy flows and understanding that and all the power system issues that go along with that. The laws of physics, as I said, just don't change. Lots of opportunities. We just can't get enough engineers that are focused on this stuff. You get a lot of people that say they are, but you know, when it comes down to utilities, we just can't get enough people for whatever reason. I don't know what it is, especially in the asset management space to look after our assets. Can't get anybody. It'll come down to understanding the physics, as I said before, but it's really about being an informed engineer, and that is having a broad view of the economics, the commercial issues, the political issues, and you know, everything else that goes around that, the social issues. And it's not just, you know, it's not just in front of the meter, it's behind the meter, it's all over the place, and the meter itself. Do we need meters? You know, it's one of those things where I think the whole industry is now being thrown up in the air, and where it will land, we don't quite know. But anyway, that's... Now, I'd recommend, there's a couple of references here, and I'll leave this. This is a parliamentary inquiry into microgrids. Our local government is doing that, not local, state government is doing that. And I recommend you look into that. If you just simply go to the WA government website and you put in microgrids, you'll come up with that. And there's a whole bunch of, there's about 100 submissions there on microgrids, the future of microgrids, the future of the industry, etc. And obviously the Finkel report, can't go past that. It's a good read if you want to get some sleep, but it talks about the neg and the reasons for the neg, but yeah, I'd recommend those two references for you guys. So that's it, I'll hand it over.
Do you have a question?
Yeah.